Today we're going to do an activity, the purpose of which is to see what the relationship is between the horizontal position and time and the vertical position and time of a projectile. We know what the shape of a projectile is, right? We know that it follows a parabola. But what is the relationship between the horizontal position and time and the vertical position and time? In other words, what are those graphs going to look like? How are we going to do this experiment? This is kind of a neat one, actually. The materials and the procedure is relatively straightforward. It's relatively simple. Here's what it's going to look like. Okay, you or your partner is going to stand with a ball in your hand, whether a volleyball or a basketball. Pick one of the balls that's up here at the front of the room. You're going to throw that ball. You're going to throw it in an arc like this so that it lands on the floor. Now, one of the other partners involved in the group is going to video this with their phone. Okay, you're not going to use the SparkView app today. That's not going to crash. You're just going to use the native video recorder that's in your phone, whatever it is, whether it's your iPhone or your Samsung or whatever it is. Record it. Make sure that you get the entire path of that ball in the recording. If you don't, then throw the ball again. Now, what else do you have to have in there? Somewhere else, we're going to have another person in there holding on to a meter stick. Now that person is going to be right underneath the path of the ball. So the person that's throwing the ball right here is going to throw the ball right over top of that person. Why do we need the meter stick in there? Well, what's going to happen is that we're going to take this video, email it to ourselves, and then use one of the computers, one of the physics computers we have, in order to analyze this video. The program that we have called Tracker will use the frame rate of your video camera, of your iPhone or whatever. From that, it'll determine how much time exists in between each frame. And then you're going to, on this program, put a dot everywhere you see the ball. So in other words, the ball is right here, put a dot on it. The next frame, which it goes to the next frame automatically, the ball's going to be up here, put a dot on the ball. The next frame, it goes to right here, put a dot on the ball, and so on, and so on, and so on. That's going to give you some data. You're going to copy that data, you're going to email that to yourselves, and then you're going to plot yourself a couple graphs to see what the relationship is. Does that kind of make sense? I'll show you how to use the program in just a second, so you're not going to be going blind into this. Okay? Bottom line is the experiment itself. Somebody's standing over here. Okay, I'm kind of standing back from the board right now looking at this situation. Okay, I'm the guy with the video camera. Okay, I'm videoing this guy throwing the ball over top of this guy who's holding a meter stick. Anybody know what the point of that guy holding a meter stick is, by the way? Yep. Yeah, the program knows what the time is in between frames because it knows what the frame rate of the video is. So knowing the frame rate of the video, the frequency essentially, it can determine how much time exists between frame. But it doesn't know how far the ball has gone. So what it needs is a definition of a meter. What you're going to do is define on the program this distance right here is 1 meter. In order to define it properly, you need to know yourself what a meter is. That's why we have a meter stick in there. Does that kind of make sense? Now the computer knows the time and it knows the distance. Now the computer can plot a data table. Here, let's just go to the next page. The computer can create a data table with time, position, and velocity. But you're going to get that for the x component and the same thing for the y component. So you're going to copy that data for the x component. You're going to copy that data for the y component, and you're going to email it to yourself. Now, once you have that data, you're going to plot 2 position time graphs. Position versus time for the x component, and position versus time for the y component. From those graphs, you're going to determine what the relationship is. What was the problem? What's the relationship between horizontal position and time and vertical position and time? What's your conclusion? The relationship between horizontal position and time is a linear relationship, or it's an exponential relationship, or whatever it is. This is how I know I know this because the shape of the graph is a straight line, or I know this because the shape of the graph is curving upwards, or whatever the case may be, right, Kate? Put it away. Your sources of error, okay, you know what to do with sources of error. Just don't forget your ways to improve it, your suggestions for improvement. So what do we got to hand in for this? Okay, notice what it had here. We started off this time with a problem. We went to materials. We went to procedure. Okay, it's the first time we've done materials and procedure, right? Okay, with the first two labs we did, we ignored that stuff because I want you to become good at data analysis, conclusion, sources of error. Now that we're pretty good at that, we're introducing a little bit more. Problem, which I gave you, the materials, the procedure. What comes next? The data, the analysis, the conclusion, sources of error. What are we conspicuously missing here? We're missing the variables. Normally, you would list the variables, the manipulated, responding, and control variables, and the hypothesis. You do not need to do the variables and the hypothesis this time. Okay, we're almost there. We're almost at the point of being able to write a good, full lab write-up. This is almost complete. Okay, next one we do, we'll probably ask you to do everything, including the variables and the hypothesis. Yep. No, that's a good question. That's a really good question. You need to keep that camera still, completely still. Now, that's hard to do when you've got an iPhone in your hands, right? So my suggestion would be have something to brace it with. You know, maybe you put your elbows on the desk like this and kind of hold the camera like this, as opposed to just kind of holding it up in the air, right, where your arms can move around a little bit. You're not going to be perfect with this, okay? But do as best as you can, because if you have motion of the camera itself, then it's going to distort the motion of the ball itself in the frame of the video, right? So you got to keep that camera as still as possible. There's a source of error though, right? Right there is that it's really hard to keep the camera completely still. Okay, what's a way to improve that? Well, I want you to do your best to improve it today, but you don't necessarily have all the equipment available to you today to do the best you can. When you're talking about your sources of error, maybe you can come up with something better if we had something else to do it with. Okay. All right, so how's this program going to work? Well, the program's going to look something like this. Okay. Dustin, question? Doesn't matter. You can, sure. Go ahead, but it doesn't matter. The video is going to look something like this, guys. The program is going to look something like this. You're going to open up right here the video that you recorded and that you emailed to yourself. So open up that video. Okay, this is the video that I have. Okay, it looks something like this. So let's get down to my computer because it's so easier to do this with a mouse than just with a smartboard here. Okay, now there's a couple of things that I have to do, and I'll give each group a piece of paper, kind of a cheat sheet as to how this works, just to kind of refresh your memory as to how the program works when it comes time to actually do it. The first thing that we're going to do here is scroll forward until the ball actually leaves the hand. You see the little ball in the person's hand there. We're going to move this video forward. Okay, ball has left the hand. Okay, now we have to set a frame of reference. Okay, the frame of reference is going to be found by clicking on this little button right here. Okay, the coordinate axis. You can see that it's right in the middle. You can set that coordinate axis anywhere you want. My suggestion would be to set it right there. That defines my first data point as basically 0, 0. Does that make sense? It doesn't have to be there, okay, but that's probably the most convenient place to put it. You can put it anywhere you want, but as I say, that's probably the most convenient place to put it. Now what we have to do is define a meter. Okay, this is kind of a funny looking meter stick, and my suggestion for you would be to put the meter stick horizontally like this instead of vertical like this, but it doesn't really matter as long as you have a meter somewhere defined in that frame. So to do that, we're going to click on Tracks. Again, this is all on a cheat sheet that I'm going to give each group here. Tracks, New, Calibration Tools. We want to create a calibration stick. And you can see that that says, it's kind of hard to see that, but you can see, I think if you look closely, that it says 100.0, 100.0 centimeters. Now that's not a meter though. 100 centimeters is, but the distance that that measures isn't a meter. So what I want to do is take the start of that meter, that calibration stick, the end of it, and line it up with the meter stick. Now what we've just done is told the computer that that's a meter, that that's 100 centimeters. Does that make sense? Now we have to track the ball. So what I'm going to do now is create an object. Click on Create. Again, this is in the cheat sheet that I'm going to give you. Create a point mass. Okay, it's called Mass A. I'm going to click on Mass A. Okay, I've got to make sure that I've got it selected. And then, when you do that, unfortunately, it seems to take the video back to the start. So we're going to have to scroll up a little bit and get the ball back to where I wanted it. Okay, there's my start again. Click on Mass A. Oops. Okay, and now what I'm going to do is click Shift and my click button on my mouse at the same time. Okay, again, this is on your cheat sheet. I'm going to click that right where the object is. Shift, click. Automatically goes to the next frame. Shift, click. And the next frame, Shift, click. I'm going to keep clicking on that ball. Until the ball goes back to where it started vertically. Okay, I'll stop here now because it's gone below the x-axis, or at least what I defined as my x-axis. You can see some data right here. Time, x position, and y position. I lied to you guys. When I showed you that, data table, I showed you time, position, and velocity. It doesn't show your velocity. That's okay. We don't need that. Okay, it shows you time, x position, and y position. What we want to do now is click on just a random point. Click on Control A. That's going to select all of your data. Control C. That's going to copy all of your data. Go into Microsoft Excel or Google Spreadsheets. Okay, Microsoft Excel probably, because that's where you're going to plot your graph. And as soon as it's in there, you're going to go Control V, which is going to paste all of that data. Now that you have your data for x position versus time and y position versus time, we're going to plot a couple graphs. Let's do the first one here. X position versus time. Select your x column. Insert your scatter plot right here. Okay, now what I want to do is select my x-axis, because for whatever reason, Microsoft Excel by default puts the trial number on the x-axis as opposed to the data that you actually want. So let's select data for the x-axis. Okay, we've already got my y values selected. Let's select my x values. Okay, done, done. Okay. Well, what do you see about that? There's my y position. There's my x position. I probably want to label that. Okay, label my axes. What's the relationship there? What's the relationship that I found between time and x position? That's really close to a straight line, isn't it? Like really, really close to a straight line. Let's add that trend line in. Display the equation. Tells us this ball was traveling horizontally at a constant velocity. Isn't that what I told you a couple days would happen? Horizontally, the speed doesn't change, right? Horizontally, this ball the entire time is moving at 161.55 centimeters per second, or 1.61 meters per second. Yours will be different, right? Okay, but something like that. Now let's do the y-axis here. Select my y variables here. Let's go insert. Let's insert my scatter plot again. Okay, I get my trial number again along the x-axis here. Okay, let's select my data for the x-axis instead of the trial number. My x values will be time, the first column. Okay, okay. Okay, let's tidy that up a little bit. I label my axes, label the title, and so on. What do you see there? What's that shape? It's a parabola, right? So what's happening here? What's happening to the ball? Okay, if this is y position and this is x position, what's happening to the ball as it's going up? You guys know this, right? This is one of the first things we learned in Physics 20. As the object goes up and it curves like this, the ball is slowing down. What happens down here? The ball's speeding up, right? The ball is going farther and farther and farther in the same amount of time. The ball's speeding up, but in the negative direction. Make sense? Okay. If you get graphs that look like this, it's pretty much done for you. Okay, if you get graphs that look a little bit different than that, well then you got to think a little bit. You should If you do this properly, you get graphs that look like this, or at least more or less like this. Guys, what I showed you was real data. Like that's the real thing, right? So if that's real data and we get results that are this perfect, you guys should get results that are pretty darn good as well. As long as, who said it about the camera? Joe, is it you? As long as we can keep that camera still, right? And as long as we've got the frame of reference defined properly and so on. Got it? Any questions about that? Yep. No, you don't need velocity. Honestly, when I typed that up, when I typed this up and I put time, position, velocity, I typed that up this morning. And when I typed that up, I was thinking of the activity we just did in Physics 30, which had time, position, velocity. So that's just a typo. We don't need velocity at all. And in fact, when I was typing it up, I knew we didn't need velocity. I was just thinking that it would give us velocity, which we don't need anyway. So that's fine that it doesn't give it to us. We're going to get time and position, but it's going to be time and position for the X and the Y axis, which is exactly the data that we need. Good there? All right.